Hello, everyone. I'm so honored to be with you here to communicate academic questions and ideas. First of all, I want to introduce myself. My name is Yifei Zhang from Academy of Mathematics and System Science, Chinese Academy of China, and improved objective programming approach to forecast combination with error discounting. I shall take no more than 20 minutes of your time and talk about the topic of the approach to forecast combination in this study. The agenda in this presentation is listed as follows. Coming to the first part, research background. In this study, the monthly WTI oil spot price is forecasted. As is known to all, the role of oil in the world economy becomes more and more significant, and oil currently occupies a leading position in energy. Meanwhile, oil is a special commodity. The fluctuation of crude oil price reflects the activity of economy to some extent. Therefore, the study of the law of oil price fluctuations and the forecast of future oil price trends are very important for all countries. And section 2 is the research gap. The topic of this study is to introduce a new way of forecast combination. Forecast combination has been a vital and widely focused field in forecasting since it was firstly used by Bayes and Granger because of its significant advantages. Nowadays, except some traditional combination methods, there are also many studies researching various approaches to forecast combination, as listed in the following, some of which can be benchmarks in our study. When it comes to forecast combination puzzle should not be ignored. In many circumstances, even simple averaging can produce a combined forecast superior to more sophisticated combinations. Previous studies we investigated in forecast combination show that they are more prone to giving different discounts to different time points according to chronological order. Generally, it is rational to think that the closer time point might contain more information, hence lowering discount effect, that is, rising higher priority when determining weights allocation. For instance, DMSPE, that is, discounted mean square prediction error method, displays this idea. This idea in this study originates from this question below. And in this study, we break the rule of chronological order and try to cluster in sample time points into several different groups based on a certain criteria. Different groups containing distinct information have different priority when making weight allocation for different submodels. And in this section, I want to elaborate the process in the study and the mathematical formulation. Basic procedure is shown as follows. More details will be elaborated next. The first step is training and forecasting for agents. First of all, each individual model should perform well in some sense. In other words, they're not so bad. The second is generating more submodels is suggested, but the diversity between them is of more importance. So how to generate various submodels? Surely for time series, we could directly utilize various metrological or artificial intelligence methods. In this study, multivariate time series is considered and 7 different feature selection methods are used, hence generating 21 different submodels with only 3 basic learning models. And in this step 2, we could define the criterion and clusters in sample time points, as is mentioned above. In this study, time points are clustered based on the forecasting performance of all individual models. And how to define forecasting performance? In this study, forecasting performance is measured by the forecasting errors of submodels. We think that the number of submodels performing well, that is with lower error, reveals the difficulties of forecasting tasks at a time point. Generally, the smaller the number is, the greater the forecasting divergence between each submodel could be. So it seems to be reasonable to regard the forecasting divergences between different time points as another kind of beneficial information when allocating weights. And let the in-sample error matrix be written as in this form, where Y and X is the matrix of the real series and the forecasting series, respectively, and Xij is the forecasting result of model J at time I, and Eij is the error of model J at time I. T is the length of the in-sample set. N is the number of individual models. Now that we have the matrix of forecasting error, let N be the set of all forecasting errors' absolute value, and then rank the elements in set N from small to large. By using quartiles, we define that the top 50% or 25%, 75% of these ranked elements represent performing well and mark these elements. Finally, calculate the number of performing well models in each in-sample time point and cluster those time points which have the same number. Here, I just want to give you an example. Assume that there are 10 submodels in total, and for each row of the matrix of errors, we could calculate the number of performing well models by marking them at each time. So we can cluster them if they have the same number. And then we could reconstruct the novel objective function. Let the vector W be the combination weight, where W should satisfy this condition. Therefore, the in-sample combination forecast and forecast error can be written as follows. Naturally, we could calculate the in-sample sum of square prediction error presented by S. Notice that S has this formula. It is easy to think about minimizing the objective function by using S directly, which is written as follows. In this formula S, it can be thought that for all I in 1 to t, the matrix, this term at time point I, is equal weighted when minimizing the objective function above. In other words, when determining weight allocation, minimizing S means that this term contains the same information and shares the same priority for any I in 1 to t. Now that all of the in-sample time points are clustered into several distinct groups representing different forecasting divergences, obviously, we could set different discounts to different clusters. Let Ti a set of those time points whose number of submodels performing well is I, and the discount parameter rho I is set to those time points in set Ti. Then we have a novel object function which is written as follows. Compared to the previous objective function, we could find that each term, the transposition of EKR times EKR, there is a discount rho I multiplying it according to the cluster Ti. So we could make a forecast combination. In this study, we say that rho I equals rho to the power of n minus I, where I in 1 to n and rho 0 is 0, rho equals 1 or 0.9 or 0.8. Now we rewrite the objective programming function. We could find that if I is closer to n, it means the forecasting divergence is smaller for those time points in say Ti. And in this study, we think the time point with smaller divergences contain more useful information when allocating weights. So the discount rho I increases with the increase of I. And the presented method can lower the impact of those time points with greater divergence to ensure that the weights are more solid and objective, especially for fixed weight decision methods. Finally, we compare this approach with benchmarks. For instance, we compare this presented method with mean operator, median operator, trimmed mean operator, and the MSP method with discount 1 or 0.95 or 0.9, and multi-granularity heterogeneous method, or just directly minimizing the in-sample sum of square prediction error mentioned above. And we apply this idea to an empirical experiment. This experiment in this study is based on the formal work of the team of my tutor and is tested by utilizing the totally same forecast results in the previous study. And this is the monthly WTI spot price. The data ranges from March 1983 to December 2018. The presented submodels are generated by forecasting WTI's oil spot price with 198 factors. 7 distinct feature selection methods are used to extract key features, and 3 basic forecasting models are utilized, including linear regression, support vector regression, and artificial neural network for each group of the selected features, hence obtaining 21 submodels in total. The submodels are combined by the method presented in this study, and then RMSE, MAE, and MMP are calculated to compare different combination methods. Finally, the MCS test and the PT test are conducted to verify the effectiveness of the experiment. As is mentioned above, these 3 top quartiles of M will be used to define performing well, where M is the set of absolute value of forecasting error. The discounting parameter rho equals 1 or 0.9 or 0.8 will be considered when minimizing the improved objective programming function in this study. From the previous study, the corresponding results can be found in the following table below. And we can find that multi-granularity heterogeneous combination method, which is ABC in this table, achieves the greatest performance. Now I may just add one thing. RMSE, MAE, and MAP are average of 100 groups of forecast combination due to the black box nature of ANN, and each ANN model is repeated for 100 times. And here are results in this study. Different sets of quartiles or discount could lead to different performance combination, but most of them achieves lower MAPE than benchmarks. Besides, to define performing well more vigorously, we construct 2 more versions of the set M. The first version is that M is a relative error absolute value, and the second version is N is the standardized errors absolute value. And here are the results in the study based on the corresponding set M respectively. The best combination set is with the top 55% of the standardized error criterion and the discounts 0.9. We also conduct 2 kinds of statistical tests. The MCS test is tested for 100 times, and we record the top 2 and 3 best combination methods at each time. And the PT test is tested for success ratio, that is directional accuracy. For the sake of simplicity, only the top 50% of N, which N is a set of absolute value of forecasting error with discount 0.9 combination method, is displayed on the MCS test, and this way is the most likely to single. The MC test is tested for 100 times as we have 100 groups of forecast combination due to ANN. Every time we record the top 2 and 3 best methods, we can find that every time the IDOP method is selected and the top 2, certainly top 3 method by the MCS test. IDOP is the abbreviation of the method in the study. And the PT test p-value of all kinds of parameter set, including 3 kinds of error processing, 3 different quartiles, and 3 different discounts are all less than 0.001, which means that the PT tests are all statistically significant. Through the empirical analysis, we conclude with the following. First, different criterion for defining performing well and the discount parameters would lead to a little bit distinct performance of forecast combination. But on the whole, the improved objective programming approach to forecast combination with error discounting presented in this study is helpful to enhance the forecasting precision with lower computational complexity. And through the MCS test and the PT test, the approach in this study, and in most of the cases, is superior to some competitive benchmark models, including average, DMSPE, and multi-granularity heterogeneous method. Meanwhile, there are also several prospects of photos. More datasets should be tested to ensure robustness. And then, here are 2 interesting questions. That is, are there other criteria to distinguish submodels performing well? Or are there other ideas to measure beneficial information content in 10 points? We know in this paper, performing well and beneficial information are represented by the scale of forecasting errors and the number of submodels performing well respectively. If so, then 10 points could be clustered in other ways and various forecast combinations could be generated. Thank you for your listening. And if you have any suggestions or questions, please feel free to contact me. I suggest that to save the time, we can chat on the app Whova online next. Thank you very much. Thank you. Okay, this is the end of the first presentation. And I would like to remind you that you could rate this student talk on Whova. Each pre-recording is required to be played in time, and if you have any questions or suggestions, you are welcome to contact me on Whova. So let's watch the second presentation of Miss Ho Yan Sen from University Putra, Malaysia.
A very good day to everyone. I'm Ho from Malaysia. The topic of my presentation is the impact of trading volume on volatility with combining forecasts. The presentation will cover the following: introduction, objective of the study, volatility forecasting models, data, empirical study results, and conclusions. Volatility forecasting plays a crucial role in the financial markets. Nonetheless, volatility forecasting methods perform differently in different types of data sets or sectors. No single volatility forecast methods that provided the best performance in all the data. Discarding one of the single poor forecast method may lose valuable independent information. Acknowledging this fact, Cran and Crotty has proposed the use of combining forecasts since in 1967. The works by Bates and Grangles have provided initial impetus to the development of combining methods, combining forecast theory. The whole idea is to get the best valuable information of two single models and improve the accuracy of the forecasting model. There are many combining methods such as simple average methods, minimum variance method, synchrage method, time varying parameters forecast combination methods. However, there are still no conclusion on the best combining methods today. On the other hand, trading volume is a major consideration factors in stock market decision process. Wong and Huang in their study mentioned that the stocks that traded at high volume tends to be less volatile than trading at lower volume. Chiang in 2013 showed that there is strong bidirectional nonlinear Grangles causality between volatility and volumes. In general, many other studies have shown positive relationship between trading volume and volatility. The objective of these studies are said to be, first, to evaluate and compare the performance of combining methods with single forecast method. Second, to evaluate the role of trading volumes in improving the performance of combining method. Several volatility forecast methods are used in this study, such as naive method, simple moving average method, exponentially weighted moving average method, Gush models, GJR models, iGush, and eGush models. Volatility forecasting methods also include smooth transition exponential smoothing method, STES, where with various transition variables such as error, square errors, absolute error, square error, and absolute error as transition variables. On the other hand, combining methods used in this study are simple average combining method. There are 4 minimum variance combining methods, where the first alpha plus beta, second and minimum variance third, and minimum variance fourth, as shown in the figures in the slide. Smooth transition combining methods also used in this study, and Gush type method combined with the trading volume, where there are 3 types of volume are used in this study: trading volume, block volume, and indicator volume. The data used in this study are S&P data, German stock index, the DAX, CBOE volatility index, VIX data for S&P 500, and volatility implied index for German market, VDAX. There are 2,000 daily logs returns used in this study. The first 1,500 observations are used for in-sample estimation, while the last 500 are used for post-sample forecast evaluation. This slide shows the in-samples result of the individual models using MAE and RMSE loss function. Square residuals is used as the proxy of the actual volatility. The results for MAE rank the eGASH as the top performing methods, while GJR has appeared to be the best performing methods using RMSE evaluation. The 500 outsample MAE results for S&P series shows that the best performing methods for one step ahead forecast was the EWMA and iGASH. On the other hand, STESS methods are the best results for DAX series. The 500 out of sample RMSE results for S&P 500 index, the eGASH is the best forecast method, followed by GJR and STESS EAE. For DAX series, the top performing methods is STESS E, STESS ESE, and followed by iGASH and STESS EAE. This slide shows the combining methods, the performance of combining methods as discussed earlier. The series used in these combining methods are GJR, DBias VIX, DBias VDAX, and S&P 500 trading volume. The result shows that for both MAE and RMSE evaluation, the second methods of minimum variance outperform the individual forecast method for the GJR series. Is out of our expectation that GASH type models did not perform better than other combining methods for both MAE and RMSE criteria. It's also shown that the trading volume provided a little contribution on improving the forecast accuracy. This slide shows the minimum variance combining methods for GJR and DBias VDAX perform better than individual forecast methods. In general, most of the combining volatility forecast methods outperform the individual methods. Minimum variance combining methods perform the best among the other combining forecast methods. And the last one, trading volume did not show any improvement of the accuracy of combining forecast methods. Thank you.
This is the end of the second presentation. A huge thank you to the speaker, Ms. Hu. Ms. Hu sent me an email yesterday and told me that she might be not able to attend the session today due to her individual schedule. But there will be adequate time for questions and comments about the presentation. You can leave her your questions or comments on Quora or email. She will check them if she's convenient. The last presentation of Mr. Anirban Chatterjee from Walmart Labs, India, will be started exactly at 40 o'clock. Is there anyone having questions? You are free to ask questions by voice or characters or just make comments. Now we have about 10 minutes till the next start. Hi everyone, time is up. I'm gonna play the final video of the session. The prediction was recorded by Mr. Chatterjee from Walmart Labs, India. Okay, let's start.
Hello everybody, my name is Anirban Chatterjee and I'm from Walmart Labs, Bangalore in India. So it's really an honor for all of us to present in front of all of you today. So we are looking forward to sharing and exchanging ideas with you. And today I'm going to present along with my co-authors and colleagues Shubhadeep Paul and Udipto Datta. So in today's talk, I'm going to give you a very brief overview of how focusing fits into larger scheme of things in Walmart and how different kinds of characteristics of data motivated us to explore this particular aspect of focusing that we are going to present today. And at the end, I'm also going to give you a very brief overview of how we have put this end-to-end focusing system into production. Why focusing? So let me tell you that time series focusing is an omnipresent problem in all spheres of retail business. So you have large amount of data flowing in daily from very different activities, business activities such as fulfilling customer orders, managing inventory and many others. And such data exhibit many different characteristics such as extreme observations, frequent regime switching, etc. And to address such characteristics, so we need to take more targeted approach in focusing. So there are many business cases where forecasting are extremely important. So here I'm going to talk about only a few of them. For example, workforce management. Workforce management has a very important aspect where focusing can play a very important role in business. For example, Walmart has semi-offline stores set up in many marketplaces such as China. So here the system mandates the customers to place the order from mobile app, and once the order is placed, the store associates are supposed to keep that item packed and ready within an SLA. Now, store associates who help in packing items are hired from an external agencies on a weekly basis. And once the item is packed, actually customers are expected to pick up that item from the respective stores where they place the order. Now, accurate forecasting of orders is extremely important from the perspective of efficient process in hiring associates, because as you can understand, right, if we can overhire people, so then it will help the organization to adhere to the SLA, but it will be an expensive option for the organization. However, if we underhire people, that will certainly cut down on the cost, but it will increase the risk of violating SLAs for maybe some of the customers, and eventually it will lead to bad customer experience. Uh, so among the other use cases, there are inventory planning. So inventory planning is extremely important to meet the ever-changing requirement of load and demand, and make sure that our inventory never run out of stock of the products in demand. Among the other use cases, there can be infrastructure capacity planning, where the IT operations team add up the design and capacity of our IT infrastructure to match the ever-changing business application requirements while operating at the lowest cost. Now, in course of our work regarding applying focusing in the workforce management, so we explored different focusing options. We explored different kinds of focusing models, and finally what we settled down with is not a single focusing model but an ensemble of focusing models. So creating ensemble of multiple independent focusing models is a well-known approach where different weights are assigned to different focusing models, and a weighted combination of the outputs of different models is produced as the final focusing output. So different strategies have been proposed to combine multiple focusing models into an ensemble framework. However, none of the existing methods perform really well when there is local distribution drift in the data. So local distribution drift is an important characteristic of many real world datasets, such as the one that we worked upon in the recent past, where especially the sales data, where the complex market dynamics cause local drift in distribution. So we need a dynamic ensemble framework through adaptive assignment of weights to different forecasters, addressing local distribution drift in the data. So the challenges involved with this process primarily revolve around two questions. How can we define distribution drift, which is extremely important? And number two is, how can we define specialization of different forecasting models, basis which dynamically different weights can be assigned to different models at different time instants. Now I will hand it over to my co-author Shivadip, so we'll take you through the details of the technical concepts of our proposed approach.
Thank you, Anirban. Hello, everyone. My name is Subhadeep Pal, and as Anirban mentioned, I will take you through the technical concepts of our proposed approach. So, our proposed approach, the dynamic weight assignment algorithm, has three major components. Coming to the first, learning of base level models. Here we train n individual forecasters independently. The objective of each and every model, say MI where I is the ith individual forecaster, is to predict the next value of the time series, that is yt plus 1, when data up to time instant t is available. It is expected that heterogeneity in the models will result in different inductive bias and different expertise against different pattern of time series. Now let us come to the next component of our algorithm, learning meta level models. To explain this, let me start with why we need a ensemble method. We do a ensemble method to obtain superior predictive performance relative to a single forecasting algorithm. But the selecting of weights of each individual expert is a difficult task. Generally, we use estimates of predictive performance for dynamically combining experts for forecasting. Now, as I have mentioned earlier, that we separately model the individual expertise of each forecasting model and specialize them across the time series. Consequently, the forecasting models are combined in such a way that they are only selected for predicting examples that they are expected to be good at. Actually, different models have different areas of expertise across the input space. And in time series forecasting, there is evidence that forecasting models have a varying relative performance over time. So here we decided to use a arbitrage meta-learning strategy that enables the ensemble to better detect changes in relative performance of models or changes between different regimes and quickly adapt itself to the environment. So we create a meta learner for each base learner, and each meta learner is specifically designed to model how apt the base counterpart is to make a prediction for a given test example. This is accomplished by analyzing how the error incurred by a given learning model relates to the characteristics of the data. At test time instant, the base learners are weighted according to their expected degree of competence in the input observation, estimated by the predictions of the meta learners. So, in a nutshell, our method segments the time series data for training into non overlapping segments and extracts k dimensional embeddings from each and every segment. To execute the task of forecasting the value at time instant t plus 1 when the data is available up to time instant t, it checks how the forecasters have performed in different time segments, and we assign normalized weights to different forecasters according to similarity of the data distribution of recent past with that of the various training time segments and their performance of the forecasters in those training time segments. Now we come to our third component, which is the drift adjustment. But before explaining the drift adjustment, let us discuss some definition and assumptions. So, in a general sense, in the context of time series, drift essentially means divergence of the probability distribution of two time segments. However, for the sake of simplicity, we assume that the data in two different time segments exhibits similar kind of distribution but with a different mean. Now, to put it in a formal definition, distribution drift is assumed to be present between adjacent time segments ti and ti plus 1 of length L if probability of the absolute value of mu ti minus mu ti plus 1 greater than epsilon is greater than 1 minus delta. Now, since we have finite samples from both the distributions, we will naively replace mean by empirical sample average. Now, let's discuss the strategy of this drift adjustment technique. But before starting with it, let me discuss the motivation behind this drift adjustment. So, in the previous step, we have mentioned that the weights of different forecasters are assigned according to the similarity of the data distribution of recent past with that of the various time segments and the performance of the forecasters in those time segments. Now, there could be a situation that no time segment is similar to the recent past. In that case, we need to adjust the drift in the distribution. So to do so, we have formulated this quadratic problem. As you can see, the objective function is given as the L2 norm of 1 by n summation k equals to 1 to n wk x k ti minus 1 by n summation k equals to 1 to n x k t j with the constants w I belongs to closed interval 0 comma b and the absolute value of 1 minus n summation I equals to epsilon.
Yifei, I don't think we can hear the video.
Can you hear me? I'm sorry. Can you hear me?
I can hear you.
There is some trouble in the volume of the video.
Maybe if you can reshare it and share it with audio as well.
Okay, I tried again. I'm sorry.
Discuss the motivation behind this drift adjustment. So in the previous step, we have mentioned that the weights of different forecasters
Can you
are
hear
assigned
the
according to the
voice?
similarity
we
of
can
the
hear it
data
now.
distribution of recent
Okay,
past
I'm
with
sorry.
that of the various
What?
time segments and the performance of the forecasters in those time segments. Now, there could be a situation that no time segment is similar to the recent past. In that case, we need to adjust the drift in the distribution. So to do so, we have formulated this quadratic problem. As you can see, the objective function is given as the L2 norm of 1 by n summation k equals to 1 to n wk x k ti minus 1 by n summation k equals to 1 to n x k t j with the constants wi belongs to closed interval 0 comma b and the absolute value of 1 minus n summation I equals to 1 to n wi minus 1 is less than equals to epsilon. So here xti and xtj are data samples from two time segments ti and tj such that xti follows probability distribution PR and xtj follows probability distribution PR dashed. And to the constraints, the former constant helps in regularization, while the later constant ensures that wx into prx is close to the target probability distribution with respect to its mean. A more generalized and continuous version of the above quadratic problem will be minimize the L2 norm of expectation of Wx into x, where x follows probability distribution PR minus expectation of x, where x follows probability distribution PR dash, such that Wx greater than 0 and expectation of Wx x follows probability distribution PR is equals to 1. Now, let me hand over to our another co-author, Uddipta, who will take you through the forecasting framework and also the results of our proposed approach. Over to you, Uddipta.
Thank you, Shubhadeep. Hello, everyone. My name is Udipto, and firstly, I'm going to take you through the proposed framework for implementing this drift-adjusted ensemble forecasting technique. So, firstly, we divided the dataset into n non-overlapping segments of equal length. Then, we perform a paired t-test of the nth segment with each of the other n-1 segments to find out which segment differs significantly in mean from the nth segment, because the nth segment is the one likely to have the most impact on the forecasts. Once we find out those segments which differ from the nth segment, we perform the drift adjustment technique on those segments, whereby we try to find a wj for segment j, which minimizes the difference in mean between the jth segment and the nth segment. Then we multiply the data points in the jth segment with wj to adjust the mean of that segment and make it similar to that of the nth segment. Now we train the forecasting models on these adjusted segments and calculate the corresponding error measures, that is MAPE, or the mean absolute percentage error in this case. Then to find out the suitable weights of the forecasters in the final ensemble, we train a regression tree for each forecaster on the other n-1 segments with MAPE obtained using a forecaster as the dependent variable and the quantiles of the segments as the regressors. Now, we use this model to predict the MAPEs for each forecaster in the nth segment using the quantiles in the nth segment, and use the predicted MAPE to come up with the weights for the forecasters in the ensemble. So once we have the MAPEs for the forecasters for the nth segment, we calculate a weighted average of the forecasters using the corresponding MAPE values as the weights and come up with the final drift adjusted forecast. The drift adjusted forecast seems to outperform the other techniques, as is shown in the comparative analysis here, which I'll get to in more detail in the next few slides. Now, to take you through the results of implementing this methodology on a dataset we used for this purpose, I'll start with a brief description of the dataset. So we used store level order volume data from multiple offline retail stores for this purpose. The data was based on the number of orders being placed on a daily basis in Walmart stores. The number of orders varies according to special occasions or holidays, weekends, etc., leading to frequent surges. And as you can see, the data had quite a few regime switches and spikes at frequent intervals. Moreover, about 20% to 21% of the data points seem to lie above the 2 standard deviation range, and about 6.5% lie about the 3 standard deviation range, thus showing that the baseline or the standard stationary forecasting models won't be able to capture this pattern. So the need for some sort of an adjustment to the standard forecasting techniques arises in order to achieve better accuracy. Now, just to give you a brief overview of the experimental setting for implementing our particular technique, I'll take you to the next slide. So we used three different forecasting techniques, namely ARIMA, or the auto-regressive integrated moving average, the BSTS, or the Bayesian structural time series, and the neural network autoregressive model, abbreviated as NNAR for this purpose. Also, a state-of-the-art algorithm suggested by Cerqueda and et al. For combining forecasters has been considered as the benchmark for this exercise. And to quantify performance, we used a mean absolute percentage error, or MAPE, as the error measure. And using that, we compared the performance of our proposed methodology with the existing ones that we mentioned here. And as you can see from the table, our method has clearly outperformed the best individual forecaster as well as the state-of-the-art ensemble method previously mentioned for more than one dataset that we tried this analysis on. The hyperparameters of this model are the window length and the number of features from each window, as is mentioned here, which can be adjusted according to the requirement to get the results that we desire. Finally, these are some of the existing works that helped us a lot to be able to come up with this methodology and implement it to get the results that we showed. So, in conclusion, our model proposes an innovative method of combining existing forecasting methodologies to come up with an approach which seemingly provides much improved results in multiple scenarios. We are really thankful for this opportunity to present this work, and please feel free to reach out to us if you have any questions. Thank you.
Okay, this is the end of the last presentation in this session. Thank you for your presenting, Mr. Chatterjee. And okay, the time seems to be inadequate. I do recommend that we could use Whova or email to get contact with the speakers. And I want to thank you again for your participating and listening. Thank you, everyone.
Thank
Have
you.
a nice day.
Thank you, Yifei.
Thank you.
Thank you. Bye.
Bye.